Homeostasis, how body adapts to challenges. Darwinism holds that only those individuals and species survive and multiply, which are fitted to their external environments. Chemical composition of a healthy body's tissue and fluids remain constant within narrow limits. These are largely controlled by the autonomic nervous system, hormones and body chemicals. The term homeostasis comes from the ancient Greek, hómoios, meaning similar, and stasis, from stasis, meaning standing. Homeostasis refers to any process that living things use to actively maintain fairly stable conditions necessary for survival. The concept of homeostasis was first described in 1865 by Claude Bernard, a French physiologist. The term was coined in 1930 by the physician Walter Kennan. He describes how the human body maintains steady levels of temperature and other vital conditions, such as the water, salt, sugar, protein, fat, calcium and oxygen contents of the blood. Similar processes dynamically maintain steady-state conditions in the Earth's environment. Homeostasis has found useful applications in the social sciences too. Example is the law of supply and demand, where the interaction of supply and demand keeps market prices reasonably stable. The human body uses a number of processes to control its temperature. It keeps it close to an average value of 98.6 degrees Fahrenheit. One of the most obvious physical responses to overheating is sweating. Sweating cools the body by making more moisture on the skin available for evaporation. On the other hand, the body reduces heat loss in cold surroundings. It does so by sweating less and reducing blood circulation to the skin. Thus, any change that either raises or lowers the normal temperature automatically triggers a counteracting, opposite or negative feedback. Positive feedback is a response to change from the normal condition. For example, if a person's temperature is raised to about 107 degrees Fahrenheit, the negative feedback systems stop operating. High fever. A person with a high fever has hot, dry skin if they do sweat to help cool it. The negative feedback systems shut down in such a case. The increased temperature speeds up the body chemistry. It causes the temperature to rise even more. This in turn speeds up the body chemistry even more. This vicious cycle of positive feedback can only end in death if not stopped. It is important to emphasize that homeostatic reactions are inevitable and automatic. It means that the system is functioning properly. A steady state or homeostasis may be maintained by many systems operating together. Flushing is another of the body's automatic responses to heating. The skin reddens because its small blood vessels automatically expand, thereby brings more heated blood close to the surface where it can cool. Shivering is another response to chilling. The involuntary movements burn body tissue to produce more body heat. Characteristics of homeostatic systems. Homeostasis refers to the ability of an organism to maintain the internal environment of the body within limits that allow it to survive. Homeostasis also refers to self-regulating processes that return critical systems of the body to a set point within a narrow range of operation, consistent with survival of the organism. Homeostasis is highly developed in warm-blooded animals living on land, which must maintain body temperature, fluid balance, blood pH, and oxygen tension within narrow limits, at the same time obtaining nutrition to provide the energy to maintain homeostasis. Homeostasis also refers to the body's defensive mechanisms. These include protective reflexes against such things as inhaling matter into the lungs, vomiting reflex as a protection to expel toxic materials from the esophagus or stomach, eye blink reflex, and the withdrawal response to hot or otherwise painful skin sensations. There is also the defense against pathogens through innate and acquired immunity. Neuropsychology. Homeostasis is a fundamental concept in neuropsychology, psychophysiology and neuroscience. From a behavioral perspective, homeostasis can be as simple as moving back and forth between sun and shade to keep body temperature constant. Assessment and behavioral response to internal state, such as hunger, thirst, and searching for mates are all homeostatic processes, many of which are regulated by feedback loops. Biological clocks help animals to adjust their homeostatic activity. Topics such as sleep, fear, and pain fall within the general realm of this. The homeostatic mechanism may be in the form of a loop, which can either be positive or negative. Positive feedback leads to more stimulation or acceleration of the process. The negative feedback leads to the inhibition of the stimulus or to the deceleration of the process. Examples of positive feedback are labor contractions at childbirth, blood clotting. Labor contraction during childbirth is positive feedback. The initial contraction of the uterine muscle leads to further contractions. Rather than inhibiting the contraction, the body tends to produce more contractions. At labor, the posterior pituitary gland releases oxytocin, which stimulates muscle contraction. At child delivery, oxytocin release is further augmented, intensifying muscle contractions. This continues till the neonate is pushed outside the birth canal. Blood clotting. The formation of a blood clot is an example of positive feedback. The conversion of blood from a liquid into a solid form entails series activations of clotting factors. As soon as one clotting factor is activated, the next clotting factor is activated. This results in the formation of a fibrin clot. In this process, the direction of the stimulus is maintained. More examples of negative feedback are thermoregulation, blood glucose regulation, baroreflex blood pressure, calcium homeostasis, potassium homeostasis, and osmoregulation. Homeostasis of blood glucose. Homeostatic regulation of blood glucose levels. When blood glucose level is low, the alpha cells of the pancreas secrete glucagon. It stimulates the liver to convert its stored glycogen into glucose by way of glycogenolysis, or by producing glucose by gluconeogenesis. Further, insulin secretion is stopped. As a result, glucose is produced into the bloodstream, thereby raising blood sugar levels. When blood glucose is high, the beta cells of the pancreas secrete insulin. It stimulates the skeletal muscles and fat tissues to absorb glucose from the blood. It also triggers the liver cells to convert glucose into stored glycogen. Also, glucagon secretion is inhibited. This results in blood glucose returning to a normal level. Blood pressure homeostasis. Another instance of negative feedback is the homeostatic regulation of blood pressure. Blood pressure is the force exerted by the circulating blood as it hits the arterial walls. The pressure comes from the heart when it creates a pulsing act. This blood pressure is regulated within the homeostatic range through the cardiovascular center. This control center has three distinct activities related to blood pressure regulation. 1. The cardiac center sending nerve impulses to the sympathetic cardiac nerves to increase cardiac output, by increasing heart rate. 2. The cardiac center sending nerve impulses to the parasympathetic vagus nerves to decrease cardiac output, by decreasing heart rate. 3. The vasomotor center regulating the diameter of blood vessels. Calcium homeostasis. The chief cells in the parathyroid glands and the parafollicular cells in the thyroid glands are sensory cells that are sensitive to calcium ion levels. The fall of calcium ions in the plasma incites the chief cells to secrete parathyroid hormone, whereas the rise of calcium ions incites the parafollicular cells to secrete calcitonin. Potassium homeostasis. The body corrects potassium levels through the action of the adrenal complex. Osmoregulation. In the case of osmoregulation, vasopressin targets the kidney to exert an antidiuretic response, particularly by promoting water reabsorption, thereby inhibiting further water loss. The human body would not be able to function efficiently if there is a prolonged imbalance in the internal physical conditions and chemical composition. The human body employs various homeostatic mechanisms to sustain its optimal functioning. Variables such as body temperature, pH, sodium level, potassium level, calcium level, and blood sugar level have to be kept within the homeostatic range. The homeostatic range is defined as the allowable upper and lower limits for a particular variable. If beyond this range, the body would soon fail to carry out its tasks and become dysfunctional. In order for the body to keep these variables within efficacious limits, various regulatory mechanisms are employed, and each of them is comprised of three general components. The three major components of homeostasis are a receptor, a control center, and an effector. The receptor picks up information from its surroundings and relays it to the control center. The control center, in turn, processes the information and sends signals to the effector. The effector, then, produces a response based on the signal from the control center. Olfactory receptor cells, i.e. receptors in the olfactory epithelium at the roof of the nose, that react to odors or smell. Gustation receptors, i.e. receptors for taste. Auditory receptor cells, i.e. receptors in the epithelium of the organ of Corti that react to sound stimuli. Thermoreceptors, i.e. receptors in a sensory cell sensitive to changes in temperature. The control centers pertain to the homeostatic component that processes impulses relayed by the receptors. Examples are the respiratory center and the renin-angiotensin system. The effectors are the target of the homeostatic response that would bring about the reversion of conditions to the optimal or normal range. Aging. Aging, a decline in homeostasis. Homeostasis is a critical element in the aging process. The extent to which the body can adapt to physiological stressors and maintain homeostasis will influence susceptibility to illness and injury and is known as adaptive homeostasis. As individuals age, the expansive ability of the adaptive homeostatic range diminishes. This decline contributes to the higher incidence of disease development among older populations. With increasing age, the capacity to tolerate stressors decreases, but remains partially modifiable with lifestyle adaptations. The successfully aging older adult maintains a high capacity to tolerate physiological stress. The person who is aging unsuccessfully generally has a low tolerance to physiological stressors. Tolerance range increases in response to exercise. It decreases with the addition of chronic disease and greater inactivity. The older individual with very low tolerance to physiological stressors is highly susceptible to illness and has low capacity to combat the effects of the illness. A bout of influenza may kill. When a person is in homeostasis, exercise results in robust positive changes with systemic adaptation. Strength and balance can increase, as can aerobic and muscle endurance. When the inactive older adult with stable chronic disease engages in exercise, positive changes do occur, but not at the same magnitude as their active counterparts. Under both sets of circumstances, a widening of the window of homeostasis occurs. It provides greater tolerance to physiological stress, thus reducing the possibility of moving from homeostasis into illness and disease.
9.
The wider the window of homeostasis is, the greater the chance of survival and of maintaining independence in physical function. One of the biggest challenges of physical therapy practice is to promote and maintain enough physiological reserve to maintain homeostasis even in the presence of large stressors. When discussing physiological changes with aging, it is important to define several terms. Cachexia. Cachexia refers to an inexorable decline in muscle wasting that cannot be arrested nutritionally. Cachexia is rapid and relentless muscle wasting that frequently occurs before death. It is associated with end-stage cancer, chronic obstructive pulmonary disease, COPD, congestive heart failure, CHF, and certain infectious diseases. Although some young adults with more reserve may recover from a cachectic state, most people do not, and rarely do older adults recover from cachexia. The cachexia of old age typically precedes death, and even though the cause of cachexia is not well defined, it is believed to be the consequence of a massive increase in inflammatory cytokines. The other term that must be defined is sarcopenia, the muscle wasting of old age. It is the progressive decrease in muscle mass and strength during aging. It is a decline in muscle strength, power, and functional quality. It has been estimated that between 22% and 33% of community-dwelling older adults have sarcopenia. For those older than age 80 years, that number is 50%, with a higher percentage for men. The underlying pathophysiology of cachexia and sarcopenia is different. Therefore, it is not surprising that they respond differently to strength training. Indeed, sarcopenic muscle is capable of responding to strength training exercise, with significant increases in muscle mass and strength. There is strong evidence that progressive resistance training has a profound effect on virtually all of the physiological mechanisms in the nervous and muscular system in older individuals, including those with mobility issues. In contrast, cachexic muscle does not respond to progressive resistance training, and physical therapy treatment to improve strength with this condition is generally unwarranted. Sarcopenia is frequently the hallmark of increasing disability in aging adults. Sarcopenia in the West. In Western society, as many as 42% of individuals over 60 years of age have difficulty performing activities of daily living. 15% to 30% report being unable to lift or carry 10 pounds, and more than 30% have some type of physical disability. Because sarcopenia is associated with increasing disability in aging adults, they should be provided positive impact through physical therapy. Physical changes occur in all systems in the aging adult. To summarize, homeostasis has become the central unifying concept of physiology and is defined as a self-regulating process by which a living organism can maintain internal stability while adjusting to changing external conditions. Homeostasis is not static and unvarying, it is a dynamic process that can change internal conditions as required to survive external challenges. Thus, homeostasis does not mean stagnation. The health and vitality of the organism can be said to be the end result of homeostatic regulation of the internal environment. The disruption of homeostatic mechanisms is what leads to disease, and effective therapy must be directed toward re-establishing these homeostatic conditions, working with rather than against nature.